This podcast is brought to you in partnership with EVA International Media Limited. Hello and welcome to Down to Earth with Terry Virts, where we talk about what matters down here on planet Earth. And today I'm super excited to have Katie Mack back, I think for the third or fourth time. Dr. Katie Mack, it's been a few times. Dr. Katie Mack is the Hawking Chair in Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, where she's an astrophysicist and also the author of the book, The End of Everything, where she talks about how the universe will end. So that's a fun read. It is actually a very fun read. She's also a pilot. She's been doing a lot of flying and I have not, so I've been jealous. And you can find her on Twitter with tons and tons and tons of followers at Astro Katie. So Katie, thank you for coming on at the last minute. We'll make this quick.
All right. Yeah. Thanks for having me. It's always nice to talk to you, Terry.
Yeah, it's always fun. And you're in Waterloo, and I know there's a song by ABBA on my playlist, and Napoleon had Waterloo, so it's a famous place, I guess.
It might be a slightly different place, but it's a nice one nonetheless. I'm really happy to be here. I've only been here a month, so I'm still kind of finding my feet. But we're about 90 minutes outside Toronto.
Okay.
Really, really fun place to be.
I was just in Toronto. I'm doing a VR spacewalk experience that is finally, after like 3 years, we finally got it done. And we're getting ready to take it out to science museums. And so I was just in Toronto finishing filming that. What a great city, especially in the summertime.
Yeah, absolutely.
It's very cosmopolitan. Canada, you think it's kind of like country-ish. Toronto is like one of the most modern cosmopolitan cities on the planet, I think.
Yeah, it's definitely one of my favorites.
Yeah, very diverse. You find like there's like every kind of person and food and everything there. It's pretty cool.
Mm-hmm. Yeah.
So there's a thing called the Large Hadron Collider. Mm-hmm. And Hadron, it sounds pretty scary. It sounds like the name of the latest Russian tank or Russian nuclear missile or something. What is a hadron? I think this thing's going to make big news, especially in the science community, but even cross over into the general public. So what is a hadron?
The pronunciation, by the way, some people say hadron, some people say hadron. I say hadron. I don't actually know if there's an official way to do it. I hear both, but it's a collection of quarks. Right? So a proton is a hadron. A proton is one of the particles that's in the center of the atom. There's the protons and the neutrons together in the nucleus, and then there's the electrons kind of around the outside of the atom. And hadron is a collection of quarks, and a proton is made of 3 quarks. Quarks are sort of these fundamental particles that make up protons and neutrons and a bunch of other exotic particles. And so protons and neutrons are hadrons, and what the Large Hadron Collider does is collides protons together to essentially see what happens. So what you do is you take protons and you put them in this long, it's like 23 kilometers or something ring, where they're accelerated to extremely high speeds, something very, very close to the speed of light. And these protons are whipped around in opposite directions on these 2 separate streams, and then they align so that the 2 streams crash into each other, and then you get a bunch of proton collisions. And the idea is that as those protons collide, they produce these extremely high energies in very, very small space, right? And that does a number of different things. One is that it kind of reproduces the conditions of the very early universe, when the universe was very, very hot and dense, and kind of different physics happens in really hot, dense environments. And so it makes a little tiny sample of the very early universe in that collision. And because you get really high energies, it kind of changes the matter and can produce different kinds of particles that are only produced at very, very high energies at very high masses. And so you can find all sorts of exotic particles. You can produce things that we can't see otherwise, that are just are not found in kind of everyday life. And the most famous example of that is the Higgs boson. So about 10 years ago, almost to the day, the particle, the Large Hadron Collider found the Higgs boson, which is a particle that's, people used to call it the God particle. There's a famous book called The God Particle that's about the Higgs boson. It's a particle that's associated with a sort of energy field that's all over space, and that energy field is called the Higgs field, and it's kind of responsible for particles having mass. So it's responsible for the existence of atoms and molecules and all of the stuff that we're made of, essentially. So it's a kind of it's a very important piece of physics, and in order to prove that we understood how that all works, how physics works, how subatomic particles work together, we had to find that Higgs boson, and the Large Hadron Collider was able to do that about 10 years ago. So we just sort of celebrated this anniversary of that discovery.
I have so many questions. Are there small hadrons?
Well, so the protons and neutrons are small.
Right. But I mean, this is the Large Hadron Collider.
Right.
Yeah.
Okay, yeah. So it's a Hadron Collider that is large.
Okay, so it's not the Hadron that's large. It's this giant 23-kilometer, like the size. Basically, if you're living in a normal town, it's the size of your town or bigger. Yeah,
I don't remember if it's exactly. I don't remember exactly the size. I think that it's. Something like that. It's 27 kilometers. Sorry. Wow. It's a 27-kilometer ring.
Right. So that is large. Right.
It's it is like I've been there. I visited. So it's at CERN, which is the sort of European nuclear physics laboratory, and I visited a few years back. And the sort of control, the sort of reception area is in one city, and then some of the experiments are in different cities nearby. Wow. Because the whole thing is underground. And what you do is, you have this ring underground, and then at various points along the ring are different experiments. And the way it works is that each, at different points along the ring, the experiment will have the protons collide, and then there'll be a detector built around that collision point to see what happened. And there are several different kinds of detectors at different points along the ring. And so, you drive out, 10, 15 minutes away to a different part of the surface above the ring, and then you get in an elevator and you go down underground to where the collisions are, and you can look at the detectors there. So
wow,
it's
cool. It's in Switzerland.
It's in Switzerland and France. So it's close to Geneva, but right. You actually have to cross the border to get right. between some of the experiments. It spans that border, and you can actually, within the CERN campus, you can cross between Switzerland and France just walking across the CERN campus.
Very cool.
Because it's
CERN with a C, right? Centre d'Essai et Recherche Nucléaire, I think, is the CERN.
I speak no French, so something like
I was
that.
a French minor.
CERN is the. Oh, really?
Right.
Okay.
Yeah. So there's this giant, and it's underground. Is it underground because like if it messes up, it'll end life on Earth or something? Well, there was some fear that we were going to create a singularity and explode the universe.
Yeah, well, okay. First of all, nothing like that can happen.
You can't make the death vacuum. What's the vacuum thing that you talk about? Yeah,
vacuum decay.
Yeah,
no, I addressed that in the book. It cannot cause vacuum decay. No, I'll get to that in a moment. But it's underground for a couple of reasons. One is to kind of shield from like just a lot of, I don't know, like background radiation that would be messing with the particle detectors. So you kind of want to have it underground so that you don't get a whole lot of like cosmic rays and stuff coming into your detector.
Okay.
It's there's some level of shielding because these things are
because
like
of dirt
800 meters underground or something.
Okay.
Yeah. Maybe not that far. It's deep though. It's maybe 800 feet. I don't know, but some of these things are pretty deep.
Can you walk inside the ring? No.
No, it's like you can access some of the detectors when the instrument's not running.
Right.
But the ring is like a vacuum tube that goes around, and the particles go through that, but there's no, I mean, there are places where that you can access the ring, and like when it's all turned off, there are places where people can go and access the ring, but you can't, like as a civilian, you can't go like
you can't just
run
go
laps or
you can't
anything.
have the CERN marathon or
No,
whatever.
yeah, and unfortunately, no. I mean, I worked once at an accelerator facility where there was a track above the ring, and like on the ground above the ring, and you could run along that track, and I did that, but CERN is not built that way. But anyway, so the other reason that it's underground is that when you get the particles going, if they get out of alignment and like crash into like the wall or something, can create a lot of radioactivity where in the place where it hits. So you don't want to be close to that when it's happening. So
yeah, because that's how nuclear power to a certain extent works, right? These protons hitting elements that could create fission, I guess.
Yeah,
it could be a fission.
I guess so, but
yeah,
but this is, I mean, this is just like, it's just a very high energy beam, right? And like that beam, when it runs into cement or something, is going to create.
Well, that's why it's in vacuum, right? If it wasn't vacuum, if it was just going through the air, they would be running into air molecule or oxygen or whatever. Yeah. Okay.
Yeah. So it needs to be a very high vacuum, and and it's sort of sent around by magnets.
Right.
That's how the arc is maintained.
There was in 1990, there was a large particle accelerator in Texas that was going to happen, and it got canceled, and there was a lot of controversy. I thought we should do it because it sounded cool, but some scientists were saying it wasn't going to get to the energy. Do you remember that? Do you know what I'm talking about? I think all
the superconducting super collider.
There you go.
Yeah. I mean, I don't know the details of why it was canceled. I know that there was some debate about whether it would be really worthwhile. It was a very expensive project, but they'd already dug a lot of the tunnels when they shut the whole thing down. So it is kind of a bummer, and it means that the cutting edge particle physics is in Europe now in terms of that kind of experiment. I mean, CERN, the Large Hadron Collider, is the most powerful particle collider on Earth, and I mean, some Americans work there, but it's, of course, it's a European project.
It's a European, right? Well, do you know what the budget is roughly, like an annual LHC budget?
I have no idea. I mean, I think it's on the order of billions of dollars, but I don't know.
Like $1 billion or a couple billion. Yeah. I mean, it's
a big project.
I was going to save this question for the end because I still want to find out what we're going to learn at LHC, but
sure.
One, it always pops up in scientific debates and in a lot of non-scientific debates. Where is money best spent? Like, where can your science dollar get your best return on investment? Is it astronauts on the ISS? Is it space telescopes? Is it superconducting super colliders on Earth? There's a wide range of how much money you spend, and there's also probably a wide range of how much science you get back. And I'll say this real quick before you jump in. I was with Mike Griffin one time, and he was talking to a group of scientists, and afterwards I said, yeah, everybody wants to do this is 15 years ago. Everybody wants to do this project. And he said, Terry, it's amazing that all the people that are going to get the money for that project are in favor of that project, and all the people who aren't going to get the money are not in favor of it. And he I think after years in the industry, he had learned something. He was a wise man in some ways, but yeah. So where's the money best spent for science besides theoretical physics?
It's a tricky question, and the way that we deal with it in the scientific community is that we have big, long arguments, and we put together committees of large groups of people to debate the utility of different kinds of science. So, for example, in
like
astronomy,
Congress, like Congress.
Yeah. So I mean, well, sort of. I mean, so
I'm being facetious.
Like but we don't have automatic factions. So in astronomy in the US, there's a process called the Decadal Survey, and every 10 years, a group of astronomers, and it's kind of a bunch of the prominent astronomers, but also a bunch of people who are kind of more rising stars in the field or whatever, get together and have this many months long process of kind of weighing the pros and cons of different projects and setting priorities. And part of the process is that they request these white papers. So if you're working on, if you're really excited about, for example, like a new X-ray telescope or something, then you and your collaborators will get together, you'll write a paper about why this is an important project, what you're going to learn, what the budget might be, why it's a good investment, and you'll submit that. And then everybody else who has a different sort of pet project will submit their papers. And then the Decadal Survey process is going through all of those submissions and kind of weighing up, what we're really going to get out of that. And so then they produce a prioritized list of the different projects, like, are we going to spend this much on a space telescope? Do we need to put this much money into a ground-based telescope? What kind of programs are we going to fund?
Real quick, who is we? Is we National Science Foundation, NASA, university? Who is we?
Well, so this is the thing. The Decadal Survey is put together by the community. So all, astronomers in industry, or mostly in universities and national labs, just astronomers everywhere, research astronomers will put together this document that gives the priorities. And then the funding organizations will use that document as a kind of guide. I mean, they don't have to follow the recommendations, but the National Science Foundation, NASA, and so on will take that into account. So like if I'm writing a proposal and I'm saying, I want money to do a research project on dark matter and early galaxies, for example. And, here's, I need to buy a computer to do this, and I need to hire a postdoctoral researcher, and I need to fund my graduate students, and we're going to have to go to some conferences or whatever. And this is what my budget is. I will put somewhere in that application, like, by the way, dark matter was identified as one of the priorities in the decadal plan, and so then it's a signal to the NSF, like, oh, this is something that was considered to be important by the community as a whole. So that's the way that's done in astronomy. And there's a similar process in particle physics in the US, where, again, like there's months and months of meetings and documents produced and letters of intent and all of this kind of thing to put it all together. And then there's a committee who kind of writes a final report that says, here's what the community as a whole thinks is important. So the recommendations are, to some degree kind of democratic, in the sense that everybody kind of gives their input, and then a community, a group of people who have dedicated a lot of time to making the decisions kind of puts it all together and summarizes it. But ultimately the people at the funding organizations make decisions. Although, to be fair, the funding organizations, those decisions are also highly influenced by just the community as a whole. So, for example, I will be asked to read a funding proposal for the NSF. Like if the NSF is, they put out a call for funding for research projects, I might be asked to sit on a committee to read, a dozen proposals for extragalactic science or something like that. And then I have to go through and read those proposals and meet with a committee. And, we are also taking into account the decadal plan and everything. And so it's really a community-wide decision. There's no like one person who makes all the calls.
It's one of the things I love about science is because at least everybody has their own angle and their own pet projects, but you're able, much better than our political system, to kind of come to intellectually sound, most of the time, decisions. Anyway, so it's definitely, it's a model for other areas of society to follow, I think. So I assume, and you're talking astronomy, but CERN is particle physics, and you're a physicist, right? You're not an astronomer?
I'm
or both.
Right. I'm an astrophysicist. I'm a cosmologist. So cosmology is the study of, the universe as a whole, from beginning to end, largest and small scale. So I'm interested in things that impact the evolution of the cosmos in general. But some of the approaches I use are more about particle physics, and some are more about astrophysics. And so I'm kind of in the middle there somewhere.
So CERN and other particles, these are particles. These are like super small things, but that affects how we understand super big things.
Yeah, yeah. I mean, it's a huge impact on how we understand the early universe because, the Big Bang Theory is this idea that the universe was hot and dense and not really, but hot. The universe was hot and dense and, in some sense smaller in the past. And then over time, it's been expanding and cooling. And so if we can recreate the conditions of that very early universe, we can learn something about what physics was doing at the very beginning of the cosmos. And so things like the Large Hadron Collider tell us a lot about that. I mean, the Higgs boson, as I mentioned, was a huge discovery. It filled in a big piece of particle physics, of how we understand particle physics, but it also told us about a process that occurred within the first, tenth of a second after whatever the beginning was, where it kind of set the rules for particle physics. It set up the conditions for certain particles to have mass and so on. And so we learn about the very early universe by doing these experiments in laboratories. So there are really strong connections between early universe physics and particle physics.
That's incredible. Like right now in my studio, I'm breathing gas. I've got liquid Coke and a solid bottle, but that physics of liquid, gas, solids was different then, I guess. Very different.
I mean, the kinds of particles that existed in the universe were different. I mean, at the,
well, it was photons, right? Yeah.
Well, so there was a time when basically, you just had photons, but then there was a transition called supersymmetry breaking. That's or spontaneous symmetry breaking. Sorry, that occurred. That's where the Higgs boson, Higgs field comes into it. And I won't get into the details, but
hold on a second. When you say that, is math just flying through your brain right now? Like, are you seeing I see equations on your blackboard.
Things, yeah.
You need math to understand this, right? I mean, you need math to understand what you're talking about.
I mean, I could explain some of this stuff more in more detail without a lot of math, but it would just take a really long time. So
that's okay.
So I'm not going to get into it.
Right.
But the point is that when this process occurred, before that process occurred, we didn't have protons and neutrons and electrons and quarks and all that stuff. There were a different set of particles. They didn't have masses, and like particle physics just looked totally different. You couldn't.
It was before quarks. Before quarks.
Yeah, it was before quarks. Yeah. Wow. And then that process happened, and then it set now, and that set the scene for how particle physics works now in our universe. And so like by understanding the Higgs mechanism, by detecting the Higgs boson at the Large Hadron Collider, we learned how matter came to be what it is in our universe, which is kind of cool.
That's amazing. We talked about Webb, which is fixing to have its first real photos. I think like it's getting ready to start doing science, which is super exciting. And it's looking, because it's infrared, it can look farther back in time because of red shifts and, the galaxy's expanding. And we go back and listen to that podcast. We talked all about that. But it's not looking this far back in time. It goes like a couple 100 million years after the Big Bang, not 10 milliseconds after the Big Bang or whatever.
Right.
You can't see that, right? You can see the anisotropy, the microwave background radiation, but you can't see that.
Right. Yeah. So the microwave background radiation, the cosmic microwave background, is the light from so I mentioned the early universe was sort of hot and dense, and you can think of it like the glowing plasma, like all of space was filled with this glowing plasma. And then as it expanded, that plasma cooled. And at some point, basically the fire went out, and that happened at about 380,000 years after the beginning. And so when we look at the cosmic microwave background, we're looking at the glow of that fire just as it was going out, essentially. Wow. And so that's what we see when we look at the cosmic microwave background, and that's the earliest sort of light that we can get from the universe. But in terms of understanding the physics, if we can make those high energy collisions, we can sort of simulate, or recreate in a laboratory what it was like even earlier.
Is there any debate? There's always debate. So you're saying we can simulate this condition at this point in time, but are there physicists who are saying, no, that's not what the earliest universe was like? or does everybody agree that that was this high energy will simulate the first milliseconds of the universe? Is there agreement on
I
that?
mean, I think there's pretty good agreement from about a tenth of a millisecond onward.
Wow.
I think that
Wow.
that from that, most of that sort of time frame is pretty well understood. There are some things that could happen that may or may not have happened, within the first few minutes. But I mean, the general agreement is that, yeah, we did have this hot dense universe, and the Higgs mechanism, this transition happened, and it's set up particle physics. Where things get a little bit more controversial is when you get to kind of before, like what caused that fire, essentially, like what created that hot plasma, and how did that set the scene for like the expansion of the universe and so on. That's where there are different theories and different discussions, and there's a sort of accepted model, but it's harder to get really good data about that.
When was inflation? Besides
So
now,
inflation,
2022, we have inflation, but back then.
yeah. So cosmic inflation, if it occurred, was within the first like 10 to the minus 35 seconds, like the
wow.
earliest moments. And then if inflation, if it happened, it was this very rapid expansion of the universe in the very first moments. And then what we think happened is that there was this very rapid expansion, and then that rapid expansion slowed down, and the energy field that was causing that rapid expansion kind of decayed into radiation, created this sort of hot fiery soup, and then the expansion continued at a slower rate, and then the sort of plasma burned out, and that's when the cosmic microwave background occurred. So there, that inflation part is part of what's not 100% like certain. So we have good reason to think it happened, but we don't have proof of that.
Right.
And so there's debate about that beginning bit, but beyond, once you're within, after a few seconds or a few minutes, there's not much debate there.
So we just had the 4th of July down here celebrating, kicking the Brits out. And so the firework goes off, and then it goes, and then it slows down and kind of, but that's not how the universe happened. It was like that first explosion was super fast, even faster than like a normal thing. And why is it that we know that inflation happened, since it was so long ago?
Well, so we don't know for sure.
Or why do we think?
So there are a couple of things that make us think that inflation probably happened. One of them has to do with kind of the shape of the universe. And that's a little bit hard to explain, but so Einstein's theory of relativity, general relativity, his theory of gravity, stated that the reason that what we feel as gravity is actually the curvature of space. So when you have a massive object, it kind of curves space toward it. And usually the picture people think of is like a bowling ball and a trampoline,
right,
and kind of things fall toward it. It's more like the bowling ball, and then the space is kind of gathered in around it, sort of curved toward it in this sort of three-dimensional sense. And so that's, we have a pretty good understanding of how that works in space. But it's possible that space could have an overall curvature, like the total, just space in general could have a curvature, and it could curve inward or outward, depending on the sort of overall shape of space. So, imagine like the whole universe is like a fabric, and it could be flat or it could be bent in some way. And it looks like, based on our measurements, it looks like in general, it's not curved at all. On the large scales, if you shine two lasers parallel to each other, they stay parallel to each other. They don't bend toward each other or bend away from each other, which was what would happen if space were really bent on large scales. And essentially, inflation is one way that you can make the whole universe flat like that you can sort of smooth out whatever curvature it might have. And you can kind of think about that as an analogy, as like, if you blow up a balloon big enough, then the surface of the balloon looks flat in a small region. And essentially, the inflation blew up the universe big enough that even if it is curved overall, the part we can observe looks very, very flat. In the sense of, parallel lines staying parallel, you don't run into yourself if you keep going too far in one direction. That
It's
kind of thing.
Euclidean geometry.
Yes. Yeah.
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 I wrote my 8th grade. Sorry. I wrote a paper in 8th grade about that.
Nice. Yeah. Yeah. So that's, it's not exactly Euclidean in the cosmology because it's expanding and there's time is wrapped up in it too. But in terms of like, take a slice of the universe in one time, it looks basically Euclidean. So that's one of the reasons we think inflation happened. There are a couple of other reasons that have to do with like how lumpy the universe was in the early times and how the little fluctuations in the cosmic microwave background connect to how galaxies formed later in the universe and a few other more subtle things. But we have sort of circumstantial evidence that suggests that inflation did occur, but again, no proof. And there have been proposals for different kinds of processes that could lead to the same observational consequences, like this flatness thing. So that's where there's some disagreement, although if you take a poll of 10 cosmologists, 9 of them will say, yeah, inflation happened.
Right. Okay, so that's kind of the background, so to speak, on the beginning of the universe. And we have this LHC in CERN in Switzerland and France. And they've since it's European, so some of the protons are French driving on the right side of the road, some of them are British driving on the left side of the road, and they run into each other. And what does that, how do we tell that they run into each other? Well, first of all, how do you get a proton to go so fast? And then once they hit each other, what do you see and what does that tell us?
Yeah, so they're accelerated using magnets. So they're kind of
real quick, Katie. Proton is hydrogen, is that right? Is that a hydrogen atom?
Yeah, so the nucleus, so a hydrogen atom is a proton and an electron kind of bound together. Helium atom is 2 protons, 2 neutrons, and 2 electrons going around. So yeah, a proton, so yeah, you take hydrogen gas, essentially, you ionize it. So you take the electron away, and then you have a bunch of protons, and you put those into some ring-shaped sort of tubes with magnets accelerating them. And so they get accelerated and faster, and then they put in a bigger ring and they're accelerated in that ring. And so that you build up the speed using magnets to push them around, basically. And to keep them, like magnetic fields and electric fields, to kind of like push them around and keep them in the right paths. And these magnets and electric fields are tuned very well so that you know exactly where the protons are going, and then you can tune them to collide at particular points along the ring. And the points where you collide them are the places where the detectors are. And so you collide them in the center of the detector, and then the collision happens, and then the debris kind of sprays in all directions, and the detector picks up the particles that are produced in that collision.
Can you see it with your eye? If you were sitting there watching it, would you see this big, or they're so small you can't even see them? Well, they're in a vacuum, so they're not going to interact with.
Yeah, they're in a vacuum. I mean, I don't know. I mean, I imagine if you took the detector away and just looked at the tube, it might be a little bit bright, but you wouldn't, like, it's all very well contained in the in the detector. I don't even know if it would be visible to the eye. It's such small scales, and essentially it's a small amount of energy. It's a large amount of energy in the sense that it's the most energetic collisions ever done on Earth. But compared to what happens in the cosmos, it's a small amount of energy. And in terms of like how much energy it is on a sort of everyday scale, I was just reading something from CERN the other day that was saying that the Large Hadron Collider was just upgraded. They just started this run 3 where they're running at higher energies than ever before. They're running at 13.6 TeV, where TeV is tera electron volts. It's a unit of energy. Previous run was at 13 TeV, and the CERN website says that 13 TeV is the energy of motion of a flying mosquito.
All right. So is
so
it fair to say the energy per mass is enormous, but the
yes.
mass is zero, so the total energy is not very much?
Well, the mass is not zero, but
It's
it's
close.
small,
Yeah.
right?
Right.
Yeah. So I mean, and it's in a very, very small space, right? So
Okay.
it's you put that much energy into a tiny subatomic scale
Right.
space, and it does a lot. But in terms of like how much actual energy compared to things that we experience every day is not
Right.
very much at all.
It's not a nuclear explosion. It's 1/2 mv squared. The V's big, but the M is really small.
Um, yeah.
But okay. So these particles hit each other. Detectors. What kind of detectors are they? Cameras or what?
There are lots of different kinds of detectors. So
Right.
there are detectors that pick up muons. There are detectors that pick up electrons, photons. They're sort of in rings around the collision site. And so as particles come through, some of the detectors have like electric fields to bend the particles around for the ones that have charge. Some of them are kind of made of materials that will absorb particles as they come in. So there's a whole range of different particle detectors built for different kinds of particles, and the goal is to catch every different kind of particle that's produced in that interaction.
Right, and they're subatomic particles, right? You're getting quarks. Are those quarks?
Well, you're not getting quarks by themselves exactly. You're getting like, you get these very short-lived exotic particles made of quarks that decay into other things. Well, they decay into just a bunch of sort of an array of lots of different things.
They have cool names. Okay, so you get this soup out, and what, like, if you were a theoretical physicist working on this project, and like you pull the paper off and you look at it, what would get you really excited? Like, what would you see that would go like, haha?
Well, I mean, generally what you need is you need lots and lots of collisions before anything interesting is visible, because each collision is just a spray of particles. And so, I mean, the one thing that would be kind of noticeable is when that particle collision occurs, a whole bunch of debris, a whole bunch of decay products come out. And these detectors can count up how much energy, how much mass is in each of those particles that's detected. And they know how much energy was in the collision. And so if there's something missing, if they detect less than the total amount of energy they expected, then it's possible that something was created in the collision that went through all of their detectors and wasn't caught by any of them. And that could be a really interesting new particle.
Right.
So that would be a missing energy signature. And that's one of the ways that we look for dark matter. Is we really hope that collisions of protons might sometimes create dark matter particles, and then those would escape the detector, but there'd be this missing energy that we could look for. So that's one way, that would be an interesting result. Of course, every individual collision, something might have just gone through the cracks, right? So you have to build up a lot of data to prove to yourself that that's actually what was seen. In general, the interesting results are, they're not going to look like anything obvious to a general observer. What you do is you add up the amount of energy in different energy bins for different kinds of particles, and you have some expectation of how that should be distributed, like how many muons of a particular energy should be expected and how many muons of a different energy, and there's some curve that defines that. And then if there's a little bump in a place you don't expect, if there are sort of extra muons in a particular energy bin or something, that could be interesting.
So it's a statistics game.
It's a statistics game, yeah. And that's how the Higgs boson was found. It was photons, but anyway, they found like a little bit of extra energy in a particular energy bin, and then corroborate it with other experiments and other kinds of particles, and that was how they found that boson. So it's it's not anywhere near as straightforward as I think people imagine. Like you don't just
Right.
see like, oh, there's that particle and it's blue
Right.
and I know that that's the one. Like it's much more sort of lots and lots of statistics.
Right. There's an instrument on the space station called AMS-2. It's a alpha magnetic spectrometer. And as I understand it, it's looking for dark matter. And as I understand it, they need years and years of data to get the statistics and look for those little blips. And so it's not like the movie Don't Look Up that was really about, it was about much deeper societal issues. They're looking at the picture and they see the asteroid coming, and it's not that dramatic of a thing, right? Yeah.
Right.
But it's pretty cool. You're looking to find the fundamental physics of the universe, which is pretty exciting stuff.
Yeah, for sure. Absolutely.
How long will it take them to do this? Like, I imagine you don't just turn CERN on. It probably takes time to suck the vacuum out, and I'm sure there's a lot of procedures you have to go through.
Yeah, I mean, so the previous run ended about 3 years ago, and then they've spent 3 years upgrading the machines, getting to higher energies, replacing magnets, things like that. And then they just started the new run a couple of days ago, and so this run is going to last about 3 years. And
oh wow, it's going to run for 3 years.
I mean, not continuously, they turn it on and off, but they'll be collecting data for 3 years in this run without, changing the detectors. And but they're going to collect more data than in both the previous runs combined, because they're colliding more protons per collision. Like they collide them in bunches, so they're going to be more protons per bunch, going to be at a higher energy. And so it's going to be much more data, and hopefully that means that there's a higher chance of finding something cool and unexpected.
I'm guessing that physicists from around the world are like watching, and you guys are probably emailing each other and having Zoom calls. Physics is a pretty international collaborative profession from what I understand.
Oh yeah, it's super international. I mean, there are like conferences going on where people are talking about what this new run is going to do. But we have to be patient. It's going to be a while before there's enough data for anything particularly exciting to come out of it, I think. So once they start data releases, there'll be a lot more buzz, I think.
Okay. So the thing that before they were looking for the Higgs boson, and to summarize what they're looking for now, they just don't know what they're looking for? They're just going to see what they find, or is there a specific thing that they're trying to see?
So there are a number of experiments. I mean, there are a number of individual groups who are looking for individual, their particular exciting things. So you can put constraints on various parts of the theories by not seeing certain exotic particles. So there are groups who are like, I'm particularly interested in this hypothetical particle, and we're going to do a search for that. We're going to comb through the data and see if we see any signatures of this, new particle. And there'll be people who are dedicated to a lot of different possibilities. One thing is dark matter, as I mentioned. So it would be great if we saw some signature of dark matter, or some signature of something that could be related to dark matter. There's also the possibility of finding evidence for higher dimensions of space, which would be kind of cool. And then any new particles, right? It may be that the previous runs were not energetic enough, and this one is, maybe this one just goes past that energy threshold, and it's going to make some particles that the previous runs were not, didn't have enough energy to create. Because basically the higher mass particle, the more energy you need to create it, because mass and energy are kind of converted to each other, and so it's possible there's higher mass particles that could exist, and by having more energy, maybe we'll start to see signs of them. It's unclear, really we're hoping to find something unexpected, but we don't know. So
that's pretty cool. It's just it's unknown territory, which is exploration. So real quick, 13.6 tera electron volts. What is that equivalent to? Is that like the surface of the sun? Is that black hole event horizon? Where do you find that level of energy in the universe?
I mean, you could find it in cosmic rays. So we're constantly being bombarded by cosmic rays from
Okay.
space. And a lot of those have much higher energies, actually. So
Oh, really?
we get
Okay.
ultra high energy cosmic rays. So one of the reasons that I tell people don't worry about CERN causing problems
Right.
is because we get hit by high energy particles from space that crash into our atmosphere at 1,000,000 times the energy of what CERN can do all the time, and we're fine. Like it
Unless you're
doesn't
on the
destroy the Earth, it
ISS,
doesn't create a black hole. Well, okay,
then you see
so
flashes in your eye.
you see, yeah. So you've experienced some of these cosmic rays that I have
Yeah.
not.
Yeah.
But the fact that like we're doing these collisions in a controlled environment, so we can look at what comes out, but they're not unusually energetic compared to what happens in space in the atmosphere coming down to Earth all the time. So there's no reason to be nervous about the level of energy we're reaching. It's just there. This is the first time we've been able to put that much energy into such a small space where we can actually look at it
And measure it. Yeah. So
Yeah.
you can guarantee, you can give a money back guarantee that this is not going to cause vacuum decay. This is not going to cause
Yes.
the Death Star explosion. And if it does,
Yes.
we'll get our money back.
Yeah, absolutely.
Okay.
100%.
Well, Katie, this is awesome. Real, I know we got to run. We're short on time.
Mhm.
The war has changed a lot of things, and collaboration in space is still happening, but they just showed a flag from the war on the ISS, and that was
Yeah.
disappointing to say the least. How has it affected the physics and astronomy community? Because obviously Russia, there's a lot of smart Russians, there's a lot of Russian research.
Yeah. I mean, I haven't seen direct effects. It's a little bit complicated right now because there's also the pandemic, and so the kind of travel that we do is curtailed. So if there would have been a big meeting with a bunch of Russian collaborators, like we're not, we don't see that yet. I do know that a lot of institutes have created policies where displaced Ukrainian physicists are welcome, for
Right.
example. So I think Perimeter has a program like that. If you're based in Ukraine and you need to be somewhere else, like Perimeter will bring you in. So there's been some of that, but and I think that certain things are going to get real complicated with visas and so on. But but because there hasn't been so much travel, I think that that's been sort of damping down some of that effect. But the thing that's more noticeable though is that there are collaborations between Russia and the US and other countries on like space instruments. And so there's some space telescope that's being delayed because it was supposed to be a collaboration, and something's gone wrong with that. Well, and so it is affecting science.
Yeah, the biggest one is Exo Mars. It's a big Mars exploration project that Russia and Europe were supposed to be doing. Europe pulled out of it. The Russians have destroyed their own space program. It's not going to recover, not for decades. I don't think they've damaged. The self-harm has been, look, what they've done in Ukraine is infinitely worse than whatever harm they've done to themselves, but they have done a lot of harm to their own space program. I know that for sure. So, well, anyway, well, thank you.
It's affecting science for sure too.
Yeah, because they're an important science collaborator. There's lots of smart Russians. They have a great tradition of science, obviously, and it's just bad. Everything about the war is bad. So, well, anyway, thank you for talking about LHC. I know we had to squeeze this in. I appreciate your time a lot, and good luck. If you figure out if it's going to explode the Earth, let me know. You got my text message.
Okay, I will.
Number.
Yeah,
just give me a heads up. And if you love the podcast. Good. Yeah, Down to Earth with Terry Virts, give us a rating and subscribe. We'll see you later.
Bye.